Good evening, everybody, and welcome to the Isle of Wight Natural History and Archaeological Society Centenary webinar series. This is the first of four. My name is Matthew Chatfield. I'm the president of the Society at the moment, and I'd like to thank you all for making the time to come to our webinars. We were going to have a whole real-life conference last year to celebrate our centenary. We just had to celebrate it for a lot longer than we were expecting. And so I'm delighted to see so many people here tonight. Now, lots of people have booked up for this event. Don't forget, there are 3 more that you can book up for. So if you think this is good, there's more to come. And also, for those of you who are not members of the Society, don't forget to have a look on our website and find out lots more about what we do and other things you can get involved in. So for now, I'll say thank you very much to you all, and looking forward to a really instructing and entertaining evening.
Our first speaker is Professor Steve Hawkins, and he's come hot-footed it from the beach of North Cornwall to be with us. Steve is Emeritus Professor at the National Oceanographic Centre just across the way in Southampton. He's been a dean there. He's published lots and lots of papers. If you just look at Google Scholar, you can see a long list even just from last year, and he's a DSc. So he's going to talk to us very appropriately with our centenary about a century-long view of the English Channel. So over to Steve.
Hello. Hello everybody. I'm as usual struggling with technology. I hope you can all hear me now. I'm going to talk about the responses of marine ecosystems to global environmental change. Very much a century-long view of the English Channel from the Marine Biological Association, but also from the University of Southampton, both of which I've worked for until recent retirement, though I'm still working at the MBA. This is work I've done with Nova Mishkushka at the MBA, who's now a member of staff at the University of Liverpool. Louise Firth, who has worked at Southampton, is now a lecturer at Plymouth. And Sally Keith, who was one of Roger's students at the University of Bournemouth, I helped co-supervise a bit, and Alice Hall that we've collaborated with, and of course Roger himself. So I'm hoping that my slides will advance. They will do if I use the mouse. Okay, so what I'm going to talk about is I'm going to give a quick introduction to the MBA that's been around a bit longer than the Isle of Wight Natural History and Antiquarian Society. I'm going to briefly introduce you to global climate change. I'm then going to talk about fluctuations in the past before the more recent rapid climate change that we've seen in the last 20 or 30 years. I'm going to outline why the marine biodiversity of the British Isles and Ireland are so sensitive to climate fluctuations and climate change, and then talk about some of the interactions of climate change with other impacts. And for tonight, I'm just going to focus on fishing and climate using bottom fish data from the MBA stretching back 100 years. And then I'm going to try to explain why rocky shores are such splendid sentinels to detect change in marine ecosystems. And then at the end, just to see how we can adapt to climate change, particularly sea level rise, I'm going to mention the need for environmentally sensitive design and sea defences, and then hopefully finish with a few take-home messages. So the MBA has been around since 1888. And it's famous for some long-term observing and monitoring of the English Channel off Plymouth, but also the broader English Channel all the way up to the Isle of Wight and beyond. And there's various time series, physical data, chemical data, plankton, zooplankton, but I'm going to just focus on the 2 in orange, demersal bottom fish and intertidal organisms. And this is from an Intergovernmental Panel on Climate Change graph. And I like this one because if you look at what's gone on over the last 140 years, not only does it show the recent rise, but it also shows there was quite a dip in temperatures in the 40s, 50s, 60s and 70s and early 80s. And if you look at the Northern Hemisphere in particular, you can see that there was quite a pronounced dip. And it's really important that when we look at climate change, we don't compare with the notoriously cool 60s, 70s and 80s, but we go back to the 1950s, which was quite a warm period. And the global scientific community has a pretty strong consensus that there's a very high confidence that that human effects have since 1750 have influenced warming, and most of this is down to greenhouse gas concentrations. And this is very much the scientific consensus. There are, of course, other hypotheses, and some of them are published in really top journals like Twitter. And I particularly like the one at the top, which is a good one, but the one at the bottom particularly appalls me, mainly because the grammar's so poor. Now, if we return to the patch of sea off Plymouth, these are instrumental data going back to the 1870s when the Navy started taking measurements, and then the MBA lab was founded in 1888, and this data has been collected by the MBA and Plymouth Marine Laboratory and other scientists off Plymouth for the last 100-odd years. And you can see there's quite a lot of fluctuation. There was a very cold period either side of the First World War. There was warming in the 20s, 30s, up into the late 1950s. And the 60s and 70s and early 80s were a cooler period. The first time I saw snow as a 6-year-old in Weymouth was during the cold winter of 62, 63. And since the late 1980s, there's been some quite recent rapid warming, and then a bit of a downturn from 2009, 2010 onwards. Now, the British Isles and Ireland are particularly sensitive to climate change because the marine life here is on a biogeographic boundary. This was first spotted by a marine biologist called Edward Forbes in the 1850s. And he noticed that to the south and west of the island, of the British Isles, there was a lot of warm water species, and to the north and east there were cold water species. We now know, due to the wonders of molecular genetics, that many of the fauna and fauna that colonised the North Atlantic actually got into the North Atlantic about 3.8 million years ago and travelled over the top of America or the top of Russia when the sea ice was last open. And these cold water forms are colliding with warmer water forms that have extended upwards from the South Atlantic. Now, the first thing I'm going to talk about is the interaction of a regional scale impact, overfishing, with global environmental change. And I'm going to talk about bottom fish. So this is data off Plymouth taken either side of the First World War when it was cold, in the 50s when it was quite warm, in the 60s, 70s and early 80s when it was cold, and restarted by me when I was director of the Marine Biological Association from 1999 to 2007. And the top graph is of breams. These are very much warm water species. These are the kind of things you eat on holiday in Spain and Portugal. And either side of the First World War, they were hardly caught at all. They were caught quite frequently in the 1950s. As a kid, I used to occasionally catch them off Weymouth Pier in the early 60s. They weren't caught so very much in the 60s and 70s and 80s. And then when we resumed fishing in the early 2000s, we caught them much more frequently. This is very much a climate signal. On the other hand, the bottom left-hand graph are skates and rays. These are really vulnerable to overfishing. They grow very slowly. They're not very fecund. They only have maybe 50, 60 young a year. They take a long time to reach sexual maturity. And these were in deep trouble even before the First World War. They recovered a bit after 4 years of U-boats in the English Channel, but it's then been more or less unending decline as they've got rarer and rarer. And these are catches not by the fishery, these are catches by the MBA's research vessels going out and fishing on the same grounds in the same way over many, many years. And just to illustrate this, the picture on the left, and you can see the net behind the crew member in the middle of that picture. This is the deck of the MBA fishing boat, a research vessel in 1963 after it had been out fishing. And you can see there's a lot of large fish there. If we do a fast forward to 2001 and 2006, you can see that the whole assemblage has been really, really restructured, and most of the fish are much, much more smaller due to intense fishing pressure. And you can do various statistics with this data, and we found a very, very strong signal of temperature influencing the composition of the fish. Forget the complicated statistics on the left-hand side, but that's basically a measure of what's in the catch. So we found a very, very strong signal of climate change in the catch. But you've always got to be very careful if you just got 3 points and you've got a big gap in the data. So we continued fishing for a few more years, and then Martin Jenner did a very nice piece of work where he compared the influence of sea surface temperature, bottom landings, demersal fish landings in the whole of the English Channel as an index of fishing pressure, and then looked at the influence on smaller fish, because again, this wasn't commercial trawling, this was the MBA doing research trawl with a covered cod end, so it caught the whole catch, not just the big things, and having a look at the effects of temperature and fishing pressure on small and large species. And generally, we found that the smaller fish tended to track climate change. So the composition of the catch of the smaller species tended to track sea temperature. But from the Second World War onwards, there was very little signal with the large species. So the large species seemed to be declining with time. And Martin did a very elegant analysis where he looked at the maximum theoretical body size of the fish. This is not what they actually grow to these days, but this is the recorded maximum. Obviously, they tend to get caught before they get to these big sizes. And he looked at the change in the mass, the amount of fish out there over time. And he showed that for the smaller bodied fish, there wasn't much change in mass. But for the larger bodied fish, there was a very sharp decline. So anything over about 2 to 3 kilos maximum body size was very, very susceptible to overfishing. Things like monkfish, things like skates and rays, whereas some of the smaller species were just sort of fluctuating with climate change. So the take-home message here is that there's a strong signal of climate change, but for the bigger fish, it's very much overridden by intense fishing pressure. So to summarise, there's been big changes in bottom assemblages off Plymouth over the last 100 years, and these would also be mirrored up around the Isle of Wight. There's a strong interaction of climate and fishing driving the changes in bottom fish, and clearly climate has influenced the advance of some of the southern species. And we also know from other work that there is very strong impacts of influence of climate on switches between cold water herring and warm water pilchard, and these go back to the Middle Ages. This is work that Alan Southwood did using historical records. So we know that pelagic fish also fluctuate in relation to climate. So I'm now going to return to my main interest, which is rocky shores, and this is work that I've done over the years, quite a lot of it with Roger Herbert. And this is me a week before lockdown last year on the shore at Lyme Regis, a shore I'd first visited in 1980 with Alan Southwood, my then boss and mentor, and I'm out there with 2 different generations of students counting limpets. And when I started working at the MBA, I was looking at competition between a warm water species and a cold water species. And I was going to do all sorts of experiments on competition between them. But when I went out on the seashore, I'd read the papers, I'd read that they were about 50-50, which was good for doing competition experiments. But when I went out on the seashore in 1980, I found they were much, much rarer than had been recorded in the 1950s. And the 1950s was a warm period. So I was actually interested in climate fluctuations influencing warm water species getting rarer, because it was actually getting colder in the 60s and 70s. So I can't be accused of jumping on the climate change bandwagon. But at that stage, we found that the warm water species found most of its range, and it used to stop on the Isle of Wight in the 1950s and 1980s, was much rarer than it had been during the balmy 1950s. So we've got a big back catalogue of records that were collected by great marine biologists, Dennis Chris from Bangor, Alan Southwood from the MBA, a fabulous French biologist who worked out of the Dinard lab on the other side of the channel, which was associated with the Paris Museum in the 1940s and 50s. And then Alan Southwood continued time series on barnacles from the 1950s. I've got some time series on limpets that started in 1980, some of which I've been continuing just in the last few days and actually today on the seashore. And obviously Roger's been working on the Isle of Wight since the late 1980s. And our aim was basically to archive data to continue and where possible restart time series of key species, show that changes had occurred, and then try to come up with some hypotheses to test on what was driving these climate change responses, and then do some modelling to forecast what might happen in the future. And the time available today, I'm not going to talk about the modelling because it's a bit boring and mathematical as well. And we had a huge database. Crisp and Southwood had trotted around all these shores in the 1950s and 60s recording rocky shore species, so it was a great baseline. And also Alan Southwood had travelled all around Ireland, and we were able to help to get some funding for an Irish team, and we were able to do some cross-border intercalibration in Northern Ireland. So returning to Plymouth, how do things respond from the very rapid warming from the late 1980s onwards? So these are barnacles. This is a dark art. There's various species of barnacles, some of which are warm water, these cathalamid barnacles. Most of these here are cathalamids. And there's also some cold water barnacles, and that's one there. And probably only Roger and I would be able to spot that because we're such nerds when it comes to these kinds of things. But the warm water species were very common during the warm 1950s. They then became rarer, less common in the 60s, 70s and 80s. And the cold water species were less common in the 50s and then became more common in the 1960s and 70s. And there was a gap. Alan Southwood, unfortunately, was made to take early retirement in 1987 due to government cuts. And I resumed counting this in 1997 when I got a job in Southampton and was a bit nearer these South Coast sites from on the Isle of Man where I worked previously. And when I started resuming these counts, I found that the warm water species in the top right were much, much warmer than even in the peak warmth of the 1950s. But interestingly, the cold water species were still just about holding in there to some extent. And this is one site that we managed to keep going despite people being asked to retire early and funding cuts. And this shows a site 500 meters from where I'm actually sitting and speaking to you in Newton Ferrers, just outside Plymouth. And you can see that the warm water species dominated in the 50s. And then in the 60s and 70s, the cold water species came back in again. And then from the late 1980s onwards, the warm water species began to dominate. And also the green line at the bottom is an Australian invasive, Alminius, now renamed Ostrominius, which came in probably on convoys during the Second World War and is now on most rocky shores in the English Channel. Now, in the 1950s and 1980s, these are all intertidal animals of various kinds, snails, winkles, barnacles, and most of these used to stop on the Isle of Wight. That was their eastern limit as you went further up the channel and entered colder waters in the eastern channel, and also less rocky shores. So the open circles are what the distribution was in the 50s and 80s. The closed circles are the kind of range extensions that we've recorded in recent years of barnacles work that Roger's done, and Roger and myself and Nova Mishkushka have found various range extensions of these species as they've moved further east. Now, some of this I think is definitely due to climate change because these animals are generally, some are reproducers. They're probably reproducing several broods a year now, whereas in the cold past, they probably only used to reproduce once a year and perhaps not in every year. So there's far more larvae being put up into the plankton and then able to spread. And these species all have larvae. The one in the top right, Patella depressor, is a very bad spreader. It never reached Ireland after the end of the last ice age. It got to England and it got to Wales, and it made a very pathetic little jump just to Southsea and Hayling Island when we resumed surveys in 2004. But some of the other species spread quite a long way. Ocelinus lineatus, which was once called Monodonta, used to be stopping large quantities at Lyme Regis, and occasional individuals were found on Portland Bill. And we found that this hydrographic barrier, Portland Bill itself, was breached in about 2004, 2005. And I found the first Ocelinus on the Isle of Wight since Roman times. There is a specimen in the museum in the Isle of Wight that was from a Roman dig. So in the 4th century AD, it was quite warm on the Isle of Wight, and it got there. And Roger found, I think, probably the same specimen about 3 or 4 months later. And they're now found quite commonly on the Isle of Wight. But lots of other things actually went beyond the Isle of Wight. And let's just find out why that's the case. Well, firstly, this is some work that one of Roger's students, Sally Keith, did. And she simulated release of larvae from the east of the Isle of Wight, and actually showed that the larvae would go westward because there's a gar off the Isle of Wight. So the Isle of Wight really is a difficult boundary to penetrate. But on the other hand, if there's lots and lots of larvae being released for a longer period of time, the probability of extending beyond the Isle of Wight is much, much greater. And the other thing that's happened as well is there's been massive coastline modification, and these species have continued to spread. In subsequent years, we found them creeping along the coast. Gibbler and Bilicalis, both Roger and I have found all the way into Kent. So there's been once these barriers were breached, there's been continued spread since probably the late 1990s onwards. And we think part of this is because there's, in response to rising and stormier seas, another facet of climate change, there's been huge amounts of sea defences built. And these are really handy stepping stones for rocky shore species, to helping them to spread further east up the channel. So there's more larvae, there's more reproduction, but there's also more artificial habitat. And I even found on those sea defences at Elmer in Bognor Regis, I actually found some Ocelinus lineatus. That's now called Faucus. The species do tend to change names occasionally. I'm actually on the paper which changed its name, which is a bit inconvenient. But we actually found quite a large number there. So we're continuing to get spread further east, even though perhaps things have cooled down a bit. But once the barrier of the Isle of Wight's been breached, things are spreading further to the east. We've even found Patella depressor, a poor spreader, as far east as Beachy Head. So we've got lots of range extensions of southern species, both in their range edges in North Wales and also their range edges around the Isle of Wight. So let's return to my first love, limpets. And today I was on the North Cornish coast, and in the 1950s, this was one of the best places to find them. Even in the 1980s, population resided there. But on the shore I was at yesterday, Patella depressor was about 80% of the population. So the southern species are really beginning to do well. Up in the north, it used to occur as far north as Anglesey. It then declined in the late 70s, early 80s. And though they're very strong breeding populations in North Cardigan Bay, the Flegne Peninsula is a really strong barrier to larval dispersal, and the populations haven't really got round there much and recovered that much. But along most of the south coast, Patella depressor is now the dominant species. And I'm going to Swanage and Portland over the next 2 days, and I can get some data from there to see how well they're doing. So these are some of the sites. The top graph shows their sort of core range in North Cornwall. They do very well, but since the 80s, you can see that the percentage of the southern species, the warm water species, has increased in all places. And even at this range edge, around the Isle of Wight, Swanage, Portland Bill and Lyme Regis, with perhaps a slight downturn in the last few years as it's maybe got a little bit colder, particularly after the cold winters of 2009, 2010, 2010, 2011. There's probably about a 2 to 3 lag phase in the recruitment of these species. Now, another facet of global environmental change is sea level rise and extreme waves and storms. This is Porthleven, another one of our study sites, which always features in the pictures because there's a convenient scale object to make the waves look big, that particular tower. And in response to rising and stormier seas, coasts are being defended, they're being hardened. And the picture on the left is in northern Italy, where the whole of the North Adriatic coast has now got these breakwaters, and it's very much happening on the south coast of England as well. Now, engineers like smooth lines, but nature likes it a bit rough. And one of the things we've been trying to do is work with engineers to persuade them to actually build in complexity, get rid of their obsession with straight lines and build in some irregularities on these structures. The top left picture is actually muscles settling in grooves, which are actually created during the quarrying process for this granite block. The limpets are in some former experimental holes we made on the right, and the bottom two panels are of natural cracks and crevices containing winkles in the rock pool. And if you're nice to engineers, you can persuade them to retrofit rock pools, because we all like looking at rock pools, and we can increase biodiversity. It's not great to build sea defences because they do really mess up the ecology, but if you've got to do it to protect infrastructure, property and lives, then at least do it in an environmentally sensitive way. And Louise Firth and Alice Hall, who works with Roger, are very good at talking to engineers and persuading them to drill holes in breakwaters. And we even managed to persuade the town engineer in, this is in North Wales, in Colwyn Bay, to put in this complex habitat block amongst his new breakwater with all sorts of different pools and grooves. And a lot of this work was actually pioneered on the Isle of Wight by Archaeology, working with Roger and Alice. And these are now being installed all over the place. And this is homegrown work from the Isle of Wight, driven very strongly scientifically by Roger and Alice from Bournemouth University. So just to sum up a bit, we've got to adapt to climate change. Even if we were really good, we all stop using fossil fuels and we stop putting in greenhouse emissions, because of the inertia in the climate system, we're stuck with climate change for the next 50 to 100 years. So I think on the next 25 years, we've got to try to manage the interactions of climate change with the things that we can do something about. Things like stopping non-native species being introduced. I mean, New Zealand's a world leader in biosecurity. Managing overfishing, the example I gave earlier in the talk, trying to make sure that we're not enriching the ocean with eutrophication. We've done quite a good job on that over the last 20 or 30 years with successive European directives on wastewater disposal. And also we've got to manage how we respond to climate change. We've got to make sure we don't do inappropriate coastal development or coastal defence, because that causes habitat loss. Because generally all these local and regional impacts, if they interact with climate change, tend to make matters worse. But I think there's reasons to be cheerful. This was a rare escape to the Isles of Scilly to do field work last September, when I was able to go to the pub, even though it was outside. I'm a glass half full sort of person, unless you're drinking with me, when it tends to empty quite quickly. But I think there's lots of reasons to be cheerful. I bought my first diesel a few years ago because road tax was zero. Not very good for particulates, but great for climate change. And when I was down getting my car serviced at the Honda dealer the other day, there was the first new generation of electric cars. So I do think we are decarbonising, and I do think that that we will also learn lessons from this lockdown. I think a lot of unnecessary commuting will stop. I mean, I'm not in the Isle of Wight, which is a shame, because it'd be much more fun talking to people live than doing it from my living room in Newton Ferrers. But I am optimistic. And finally, just to sum up, you mustn't consider climate change in isolation. You've got to consider other things like fishing pressure, non-natives, habitat loss in particular, pollution. You've got to manage these interactions. Rocky shores are great. They're easy, cheap to sample, good ID guides, plenty of past information. We know a lot about these species from a lot of experimental work on the mechanisms driving change. We can use dead easy, quick and dirty methodology, 50, 60 species, and we can map abundance. You can easily survey things annually, which is what I'm doing at the moment. And if you've got broad scale long-term data, you can separate out global change from local changes like pollution. You can show whether marine protected areas are working. And also it stops you making erroneous interpretations of impacts and recovery from pollution, which can be done unless you've got this long-term and broad scale contextual data. And obviously after an initial professional phase, there's a great opportunity to translate into citizen science for a limited suite of easily identified species, particularly using the power of the smartphone camera and GPS to actually validate and authenticate and provide virtual voucher specimens of what people are finding in the field. But I still think that we need to have annual professional surveys for quantitative data and for difficult to identify species such as barnacles and limpets, which not everybody can do. I suppose these days I'm a citizen scientist, I'm not getting paid anymore, but I still feel I have to get out and continue these time series. So thanks very much for your attention, and hopefully there'll be the opportunity for some discussion at the end of the session. And I'm going to stop sharing my screen now.
So thank you very much, Steve. Now do keep your questions well, we need questions, and if you can put them in the chat, that would be great. But we're going to collect all the questions together at the end. So after all three speakers have spoken, then we'll do the questions. But do please put questions in the chat. Now, for our second speaker this evening, it's our Martin Munt. And Martin is an alumni of the University of Portsmouth, and he's worked both in Portsmouth and in Dinosaur Isle, and before that in the Geology Museum that was above the library. And then he had a 12-year break, as it were, when he did lots of commuting up to London to the Natural History Museum. And there he was the head of paleobotany collection. But fortunately, he came back to the island and is there at Dinosaur Isle, looking after it for us. So thank you very much, Martin. And he's our second speaker this evening. Thank you.
Can everybody see that? Can I have a... Okay, great. Okay, good evening, everybody. I'm here to talk to you about deep time climate change, which of course is controlled by many things, mostly the movement of continents, but also amount of atmospheric oxygen, etc., etc. So it's changed over a very long period of time, and specifically related to the Isle of Wight. Now, the approach I'm going to take is actually quite chronological. We'll start at the beginning, work to the end, but we'll throw in a little bit of history about the Isle of Wight's geology and how we interpret the geology as we go. Okay, so hopefully you can see, maybe you can't. I put up a book. It's called The Guide to the Natural History of the Isle of Wight by Maury. And I'm going to use that as my starting point for the talk. Okay. And can you see, hopefully you can all see the stratigraphic column, which I took out of that book. And we see some very, very traditional stratigraphy there of how the Isle of Wight's geology was divided. Now, before I go any further, I'd say the Isle of Wight is really very special. It is a limited time slice of about 100 million years, bit of a gap in the middle there somewhere. But it was really special because we have the most wonderful terrestrial lower Cretaceous. We have very continuous exposures of the Cretaceous, and we have unique exposures of late Paleogene deposits, which you can't see anywhere else in the world. So that's really quite special. Okay, so let's start with a little bit of historical stratigraphy. 1908, something like that, 1908, Arthur Rowe came to the Isle of Wight as part of his series of looking at the stratigraphy of the chalk in the UK, well, specifically England, the coastal of England. And you see a series of fossils there that he would have very readily recognised. You've got a Macresta, you've got a Marsupites, and you've got a belemnite called Belemetella mucronata. Now, these are what we call zone fossils, okay, biozone fossils nowadays. And historically, we would have used zone fossils like these to divide up the sequence, and the chalk is a classic example where zones have been done. Now, this was how it was done about 100 years ago. This is how it's done now. It's a very, very different looking thing. It's far more complicated. We now use lithostratigraphy, which is a mechanism for dividing up rocks based upon the rock characters. Now, the chalk stratigraphy is quite unique. Different methodologies are used on understanding the chalk, but you will see on the left-hand side there of the screen lots of marker horizons like bands of flint, bands of marl. All of these things help us are used to divide up the chalk. Of course, still with some fossils thrown in as well, because there's all sorts of stratigraphy that you can come out with fossils. Okay. So, if we are to understand how climate has changed in the past, using the rock record, there are some quite fundamental things to look at first. Okay, and I think with almost within the history of this society, this is just a little bit outside, yes, some very major discoveries have come about which have helped us understand deep time. Okay, and in many respects, this gentleman here discovered deep time, Arthur Holmes. If you're over 55, and did geology O level or A level, you probably used Arthur Holmes's classic work, Principles of Physical Geology. So you'd all be familiar with his work. But Arthur Holmes's real legacy, apart from that wonderful textbook, is radiometric dating. Okay, this is quite primitive radiometric dating, but for the first time, geologists were able to say, well, this is millions of years, and it's many millions of years. And that is what Arthur Holmes' main legacy is to us. And because of this discovery of deep time, we are able to better understand the past. So that's that was the first big revolution of the 20th century as regards geology. Here's the second one, the discovery of plate tectonics. Now, the notion that continents have changed their distribution over the planet over time, there is a historic background to it, but probably really we have to jump to the 1960s with lots of undersea exploration going on, mostly by the American Navy, US Navy. It became very clear that there were mechanisms that could explain the distribution of continents. And you'll see a series of maps on the continent maps on the left-hand side of the screen there of how we now look at the continents. Okay, amazing distribution of continents to be seen there. And this really is the one I think that more than anything enables us to understand the climatic change. It's what we call the Hack curve. Really, technically, it's the Hack et al. Curve of 1988. Now, I'll come back to this one in a minute, but what you're looking at there on the screen, and I hope you can see the mouse move, is the first attempt there to map out sea level change over time. Now, this is ranging from the Jurassic to the present day, and you can see the massive peak here that we continue to recognize in the Cretaceous, okay? The time of the global greenhouse, as we often think about it today. Now, traditionally, and these are some fossils from the Isle of Wight. This here is Holocystus elegans from the Lower Greensand, some Potamoides from probably the Colwell Bay member, and a nice freshwater snail from maybe the Bembridge, no, probably the Eden Hill limestones. Traditionally, we could look at rocks and we could say, yes, there is change in paleosalinity. We can measure that by looking at the fossils that we find. Now, this is a deliberate choice of fossils here. Corals are only found in marine settings. So it's a nice generalization, which tells us that the rocks are marine in origin. Some things, of course, will not tolerate salinity, such as Planorbis up there. So that's an entirely fresh water, though perhaps in a limestone it maybe wasn't so fresh after all, but it would not have had salinity. But then you get the bit in between, occupied by those little snails, which have always fascinated me throughout my working life. Those snails that live where the sea meets the land, and where the salinities change an awful lot. So we can use these types of animals to help us understand the past, and that's how we have traditionally determined, well, certainly environmental change, if not temperature change throughout geological time. Now, I'm no expert on the radiometric dating, which we're going to focus on a little bit now for the rest of the talk, but there it is there. Please don't ask me to explain it, because I can't. But in short, I've always thought of it in relation to two buckets. One empties into the other, and it's the time, and it's the percentage of difference between the two buckets that tells a little bit about, what tells an awful lot about time. Okay, just let you reflect on that for a moment. Okay, the Lower Cretaceous. So here we go, nice, complicated, typical geology. Here, there's the Hackett-L curve over on one side. And on this side, we see, I'm just going to see if I can lift this. Oh, I can't lift this up and move it. Oh, yes, I can. Oh, that's clever. Right. And here we are looking at the Lower Cretaceous. So in relation to the Isle of Wight, you are looking at the Bohemian, which is here, all the way through to the Albion as parts of the Lower Cretaceous. Now, there's a possibility that we may have Alterrivian on the Isle of Wight, but it's yet to be established for certain whether some of that is. And over this side here, we see landward, and in short, we see sea level change. So we start with a low sea level in the Bohemian, and then we see the gradual onset of increased sea level rise. Now, historically, we would have called this the Great Cretaceous Marine Transgression. If you I am deliberately using Sandown Bay here as my background. What you see at Sandown Bay, you see the Cretaceous Marine Transgression. You walk down at Yaverland, you walk through the Wealden, the Wessex Formation, deposited on the land. You go for the Vectus Formation, which is where I like to be, which is that bit where the land meets the sea. And then you go into fully marine conditions. And then by the time you reach the chalk, you go into quite deep offshore waters. So that's what we call a transgression, and it's always been recognized as such. Okay, the marine transgression. And before I move on, we'll talk a little bit about the Wealden. Why is the Isle of Wight special? Well, it's special for so many reasons, really, but geologically speaking, and relation to dinosaurs, the Isle of Wight has a very, very special time slice in the Wessex Formation. It's the Lower Cretaceous. It's a time when the global dinosaur fauna was changing quite dramatically. We see the end of things like stegosaurs, and we see the arrival of ankylosaurs, the arrival of the ancestors of Tyrannosaurus rex, the arrival of spinosaurs such as baryonyx. So it's a really critical time in the evolution of dinosaurs. And we are lucky in the Isle of Wight in that we have so very many, the fossils are so abundant. And I would argue that when we think about the Isle of Wight, there are some very special things on the Isle of Wight, and I wouldn't want to say that other things are more important, but this is really, really special, and we are so very lucky to have it. Okay, after the Wealden, we go to the Lower Greensand, and the Lower Greensand, I mean, you're here, we see a big Trapeum type ammonite, classic perna, and a nice scallop there. All very typical examples of a marine environment. The fact that you have things like ammonites means that it's probably a little bit offshore, because they probably didn't come close to shore unless they were already dead. And so, through looking, straightforward, traditional looking at the rocks, you can tell that the rocks had gone from the freshwater terrestrial environments of the Wealden to the typical Lower Greensand Sea, which the island was famous for. And then, of course, we jump to the Upper Cretaceous here. And again, there's a very complicated bit of stratigraphy here. If you look at, what do I want to say? I'm going to just drag this out of the way so I can see what I'm talking about. Here we see the whole succession of the Cretaceous now present on the Isle of Wight. At the bottom, you can see the Albion, which is Upper Greensand, Cenomanian, which we would, in old money, we would call it the Lower Chalk. Okay, the Middle Chalk, and then what we call the Upper Chalk. And the Isle of Wight has a time slice which covers basically the Albion right through to about the middle of the Campanian there. Okay? We have no restriction locally. Get out in the English Channel, that will be there somewhere, but none of that on the Isle of Wight. So we don't actually see the Cretaceous tertiary boundary on the Isle of Wight. Wonderful for fossils. If you're particularly interested in ammonites, you'll see here we have a beautiful scaphited ammonite here that's found on the Isle of Wight, and a more pretty one from North America there, just to give you an idea. So again, we see sea level change and the Hack curve there. We can see that in modern interpretation isn't that dissimilar to the Hack curve, but what we now have, we have the detail. Okay, we have the detail that the Hack curve does not have. And of course, the chalk, wonderful for fossils. Typical micrasta here, just to give you a feel for what the typical chalk fossil on the Isle of Wight is. And we can always dream of finding mosasaurs on the Isle of Wight. There are a few, but not many finds of mosasaurs. So, but I thought that I put it in there just to give you a feel for what would have been the thing. They were here, undoubtedly they were here. Their remains are just very rare because they just didn't preserve. Okay. Oxygen isotope curves. Yeah. The tertiary, or the Paleogene, as we should really call it, is a time of, well, when we can understand an awful lot more about climatic and sea level changes. The reason for that is the fact that most of the North Atlantic is underlaid by rocks that are of equivalent ages. They're Paleogene rocks. There are the odd bits of Cretaceous out there, but essentially the North Atlantic is underlain by Paleogene rocks. And the study of those sequences has enabled us to make a really understand how the rocks that we see exposed on the coast can be interpreted and what they really truly mean. And the chart that you can see here, now again, just to help you understand what's present on the Isle of Wight, we have a tiny little bit of Phoenician on the Isle of Wight, tiny little bit, Redding beds. We have plenty of Euprasian, Lutetian, Bartonian, and Priabonian, and a little bit of Rupelian. Okay, so if you were to go to Whitecliff Bay, you can walk, apart from seeing the top of the chalk, you can walk all the way through to the Priabonian. The Rupelian on the Isle of Wight is represented on the north coast around Cranmore, Hampstead area. It's tiny, and again, it's unique bit of geology. You can't see it anywhere else in the UK, as indeed the Priabonian. So what we see here, of course, is we see global warming in the early Eocene. Okay, there had been a bit of a cooling in the late Cretaceous, and there's a lot of debate about the late Cretaceous on whether there were ice caps. What is interesting is that traditionally it was traditionally thought that there were no ice caps during the late Cretaceous. It is greenhouse Earth. However, there is sea level fluctuations. For sea level fluctuations to occur, something must be happening. Okay, there must be something locking up water, probably ice locking up water. There's obviously thermal expansion as the world heats, but there's just a little bit too much. But what we see throughout the Paleogene is a really huge change that leads us to the present day. Okay, and I'll just point to something here. Look here. Do you see there? Just there. This is the Priabonian. So if you were at Whitecliff Bay, sorry, no, let's say Headon Hill, you would be over here somewhere. You'd be lower down Headon Hill. If you're at Gurnard or Bembridge, you'd be about here. Okay. If you were at Hampstead, you are there. And what this point represents, it represents something quite amazing. It represents the first time that we can say for definite that there is an ice cap in the Northern Hemisphere. Okay? Big change in the sea level occurs here. And it also is marked with big faunal and floral changes as well. Complicated now, very complicated. Now this is some recent research. Sadly, I wasn't involved in it. I'd love to have been involved in this. In which this is actually an attempt to, and a very successful attempt to link the terrestrial sequence that we see in the cliffs of the Isle of Wight with that Atlantic record. Okay, it's not just the Isle of Wight. You've got the Paris Basin there as well, which shows great comparison with the Isle of Wight's rocks. And for the first time here, we actually see the use of the calcite in these very common shells to map out changes in sea level, which are reflecting changes in temperature, and compare the ocean record to that of the land. And here on this side here, you actually do see here the Isle of Wight's sequence here. Okay, and actually, and what this does identify also, it does identify also that Well, very often we think of it as a rather stepwise change in sea level, okay? And that stepwise change reflects global climate. So nice and warm in the Eocene, cooling up, well, staying nice and warm, then cooling off quite dramatically towards the end of the Bartons, okay? And then another step at the end of the Priabonians. So what we kind of see is a step-like change in temperatures, global temperatures, as we see that the formation of ice at the North Pole. And there you go. Again, this reflects that. It's that same sort of data. Okay, a bit hard to understand this data, but there you go. For those of you a bit more familiar, want to see some fossils, here's some fossils. This one, hey, if you were in the North Coast of the Isle of Wight, I'm in Cowes, so if I was sitting in Cowes, this is what Cowes might have looked like about 38 million years ago. We got these nice Anthracophory type things down here, pig-like animals in this beautiful swamp. Okay, so we get the wonderful fossils, we get the turtles, we get the mammals, and of course for me you get clams as well. You know, so that is a kind of view very much of what the North Coast of the Isle of Wight would have looked like as the first ice sheets were forming over the North Atlantic. This is a wonderful graph, which I encountered for the first time only a few weeks ago, so I stole it really quickly. Here we see what really, you know, it's a wonderful graphic showing the change from the hothouse Earth of the Eocene through to over here where we live today. Well, they've got the Holocene, Pleistocene here. Can you see the wonderful record of environmental change? And you see here, that's what we see on the Isle of Wight. That wonderful jump, reflecting the first serious glaciations. Talk a little bit now about the Quaternary. We all have wonderful images of the Quaternary. This may be a Sandown, I don't know, 12,000 years ago. Could be Sandown, mammoths rolling around in the thing. So that's our typical view. Now, I've always found the Quaternary a little bit more complicated. Now, you see a nice map of the Isle of Wight here. This is from the latest geological survey notes on the geology of the Isle of Wight, mapping out the different gravel terraces and deposits that date to the Quaternary on the Isle of Wight. And with the Quaternary, we see more detail in the change in environments, changing temperatures, and changing sea levels, linked clearly to glaciation. And on the Isle of Wight, we have a little bit down here, we have a little bit here, a little bit there, a little bit there. And the reason I keep saying a little bit is because what the Quaternary is about small deposits. It's not about extensive deposits that we see, certainly say with the chalk, which is going on for hundreds of miles of, if not thousands of miles of deposition being recorded. We see local, intimate little pictures of the past with the Quaternary. And but what they do tell us about the changes that have occurred in the immediate past and those that could occur in the future should well, global warming or cooling occur. The changes in the environment that we could see. So it's a good way of looking at it. Another good way, sadly, we don't have something called the Pliocene on the Isle of Wight. Now, the Pliocene represents maybe about 5 degrees centigrade warmer than we are today. And that would make a good analogy for looking at comparison what could happen if we had serious global warming. Quaternary up and down, here we see it here. Present day over here, relative to sea level change relative to the present. There it is there, the present, and you can see the ups and downs. Ice really does lock up seawater. It locks it up and then it releases it. And you see here, it says meltwater pulse here. That's when the world changes dramatically. Okay, now I'm going to finish up with a little bit about the evolution of the island. Because I would like to call it a 20th century thing, but I think it's a bit more of a 21st century thing, though the first evidence came out in probably towards the end of the last century. And that is how we interpret how the island has formed. Okay, so we're going to a little bit about structure here. Now, this here on this side here is a quote from the geological Memoirs of the Isle of Wight, dated 1921. And I just want to point out here, Mr. G.W. Lamplugh found a slab of bored fossiliferous Cambridge shell measuring he found these at Little Stairs Point. Okay, Cambridge shell is late Jurassic. So they make a really interesting observation here. It's they're basically saying that when the Cretaceous rocks were deposited, there was erosion of Jurassic rocks nearby. Okay, it was identified that long ago, but it's only over the last probably 20 years or so that the significance of this sort of observation comes out. And it all begins with this here. I'm just going to pull this over there as well. The Sandhills Prospect. I apologize for the quality of this. I think it's probably about 200 kilobytes or something like that of information that's in front of you here. But this was given to me by one of the geologists working on Sandhills boring when it was first suggested there might be oil under the Isle of Wight. And this is the first true reflection of what lies underneath the Isle of Wight. Now, when I was at university, you were taught that it was a simple layer cake with a slight bend in the middle, making it a monocline, which was all very well and true, but it's actually a far more complicated story than that, far more complicated. And what this showed, it showed us that the Isle of Wight is underlain by a series of faults. Here they are here. Some of the faults trend east-west, some of them north-south. It's the east-west one that's really, really important, because that sits underneath the downs of the Isle of Wight. And that has controlled the geography of the Isle of the area we now call the Isle of Wight for probably about the last 350 million years. And that is why Lamplugh, back probably in the 1890s, thinking it's Lamplugh, discovered bits of Cambridge clay rock on the Isle of Wight. And indeed, since then, many other different rock types found in the Isle of Wight, because what this showed for the first time is where the chalk now sits, there was a line of hills. And these hills were eroding. They were late Jurassic rocks eroding away and supplying sediment to the south of the Isle of Wight. Now let's see a little bit more. Okay, so this most recent revolution in our understanding of the origin of the Isle of Wight is really all about faults. Now, the faults that were established 300+ million years ago were formed when the original Atlantic Ocean closed before starting up the new one. Now, why is the Isle of Wight here? Now, again, back at university, back in the day, we understood that the Isle of Wight was formed as a result of the outer ripples of the Alpine erosion. And this is a nice bit of Alps there. I can't remember what it's called at the moment. It's just completely escaped my head, that mountain. And that's what we've widely believed since. However, more recently, it's been suggested that the formation of the North Atlantic Ocean over the last 50, 60 years is actually the real cause of the origin of the Isle of Wight. It is possible that as the center of the ocean spread away from the UK, that a series of blobs of hot magma have been left behind, sitting underneath the UK. And certainly, and the suggestion is there's one sat under us today under southern England. So you might imagine this has been under southern England. Don't worry, we're not going to get any volcanoes pop up because it's long since past its effect. But the suggestion now is that the origin of the Isle of Wight is largely down to the movement of hot material underneath the continental crust. Okay, I'm going to finish up there because somebody else wants to speak, I believe. Don't know why, but they're going to speak. Yeah, of course I know why. Gary's a super speaker. Now, just for you, there are a series of references where you can get this information from. For those of us who like the old stuff, Burion's prehistoric animals for the pictures. You can get information about the geology of the Isle of Wight from here. If you want to be really, really up to date with the geology of the Isle of Wight, you must acquire this or see it. We have a couple of copies at the museum. If you ever want to come by and see it, this is the revised Stratigraphy of the Isle of Wight. And I'm going to stop there. Thank you. Thank you for listening.
And now for our third and final speaker, it's over to Garry Momber. Garry is the director of the Maritime Archaeology Trust, and he's been involved with the island for a long time. The trust was formerly called the Hampshire and Wight Trust for Marine Archaeology, and a lot of work was done in the Solent, a lot of archaeology, but the Trust has widened its interests, and indeed now they've got a commercial arm to them. But Garry's done an impressive number of publications, and he's going to talk to us today about the Solent. So over to Garry.
Right. Well, thank you very much for inviting me to talk at this salubrious occasion. I'll be talking now about archaeology and coastal change based around the Solent, but we're doing this work at the moment as part of an Interreg 2Cs project, one of the last European ones I think we're going to have for a while. It's called Sustainable and Resilient Coastal Cities, and the acronym is SARC. So there's the issue here, which we've really touched on. It's looking at ways best to protect cities as climate changes. And there's the need to try and understand that change and maybe look for sort of nature-based solutions in the future. And we've introduced archaeology to this process by saying, look at the archaeology in the landscapes, they can actually give you an insight into past change, and it can demonstrate how earlier, you could say, natural solutions form natural defenses. Now, this takes me on, after Martin's wonderful talk, into the end of the Pleistocene, the Quaternary, the last sort of 125,000 years when sea levels were much higher. Coming forward in time, sea levels were higher, then they dropped. Then about sort of peak of the ice age 20,000 years ago, they're 120 meters lower than today. Then they started to rise, and as they rose, they knocked down the hills, talking generally, then to knock down the hills, but then they filled in all those deposits, filled in all the river channels, and all the sort of valleys were filled in with sediments. In many places, these sediments that filled in these valleys tended to preserve what was underneath. So to a certain extent, when you go down the beach, you're walking back in time. And that's important if you can find evidence and date it from the past. So if we look at, I haven't got time to that one again. If we look at the Isle of Wight, of course, right, which you know well, I'm now going to show you examples of where we found that archaeology buried within sediments. Boulder Cliff, we've already had a minor reference to it earlier in the talks about Boulder formations. Boulder Cliff here, where we have the oldest boat building site in the world, and then go across to a few places, Cadland, Thorns Bay, which I'll start at, and Lymington, just to show you examples of how we can look at this archaeology and old land surface to try and help us understand past change and the process of sea level rise, and how we can get relatively high resolution of the impact of that through time. So when we look off the ferry at Lymington at low water, we can see an awful lot of mudflats. Of course, these mudflats were quite extensive around the Solent. If you look 200 years ago, they were sort of 3-4 times what they were today, and they've recently been eroded away. But under the water, we can actually see the old land surfaces that may be sort of 5,000-6,000 years old, showing that the loss of these mudflats is a relatively recent phenomena. But as it does so, it indicates there is modern change, and also it starts to reveal old land surfaces that we can date. But when we just go up the Solent, this is towards Cadland and Thorns Beach off the Beaulieu Estate here, we see that a lot of those mudflats are now totally gone. So while at Lymington they still exist, here they're totally gone, they've all moved away. And what you have is when you're walking on the seabed there, you're probably walking on one of those Eocene surfaces, whereas only 50, 100 years ago, they would be covered in more recent mudflats. And we know that's the case because we can find the remains of old landscapes that were there that covered the shores of the Solent before sea level rose. As the sea level rose, it covered these areas, it covered them in silt and sediment. And as it did so, it preserved them and protected them. And here we can get trees with bark on, so well preserved. I'll show you some examples in a minute that date back many thousands of years. And this particular spot on the northwest Solent is a Neolithic landscape dated to over 5,000 years old. And in amongst it, we have other archaeological evidence as well. This is 25 meters away from those trees, and we have some Roman occupation sites there. This would have been sort of a platform. At the time, it would have been a bit lower, Sea level, this is at low water, so at the time it was built, it would have been underwater, probably covered by about 2 or 3 meters of water at high tide. Structure, not very robust, not the sort of thing you'd normally build out in the middle of the Solent. So we're probably within mudflats protected during the Roman period. Then we go back a bit further back in time. This is 1500 to 1400 BC. And in fact, I've just been down to see this about 2 hours ago, which is now pretty much gone. But this is coming out of the earlier land surface, a Bronze Age structure, again, just above low water at the moment. So it would have been at high tide, going back to the Bronze Age, covered by about 3 meters of water. So it's a direct indicator of what would have been a much more sheltered area at the time, otherwise it wouldn't survive. But it also gives us a stark demonstration today of the erosive processes along the northwest shores of the Solent. It wouldn't be there, and it won't be there in about a year's time. It wouldn't be there if it hadn't been recently exposed and to be lost. So we can look at the sediment. We can look at well, I'll go back a bit further back in time a second. Just around the corner from there, about 150, 200 yards away, 300 meters away, we have an old Neolithic landscape as well. These are the timbers that are coming out near the trees, dating to, let's say, over 5,000 years old. Pieces of work timbers. So just in this small area alone, you've got quite a collection of material. This particular piece, you can see it's a post, but it's been covered by some form of resin, which would have been put in place to sort of protect it as the sea level was rising. Because we then took analysis of the landscape. This is a digital terrain model looking down on top of the landscape. There's in the middle here, you have a shingle bar. And then from the bottom, you've actually got this old channel, like one of the channels in that video that was filled in with sediment. And in the middle, you've got the sediment on the left here and the right, left and the right, the east and the west. You've got these peat deposits with the trees I just showed you, and the posts came over here. The Roman material is just over here. So you've got this material within the land surface, and the land surface itself, we say dated to that 3,200, 3,026 to 3,200 Cal BC. Oops. But when you go down and look inside the channel, we worked out that date when the sea level actually came into that channel, being about 30 centimeters lower than the surface, and that was at 2,571 to 2,347 years BC. And Dr. Rob Scaife on the island is looking at some pollen from those examples at the moment. Now, I mentioned that date because we have the land surface that's covered in sort of alluvial sediments. So we've got the interface between the land and the sort of alluvial estuarine water as it came in. And so we can get a nice accurate date of that rise, that point in time when sea level crept up the beach. And that comes in at about chart datum, actually, when sea level was there at that time. So we know 4,500 years ago, it was about 5 meters lower than today at high water. Jumping out here. And we can look up the beach at Cadland. It's jumping automatically. We look up the beach at Cadland. Another interesting site, going down the bottom of the beach. Again, we found another Roman structure. This just came after the, in the 1st century AD, right at the bottom of the, quite thin, you see, but exposed at low water, at high tide. In the Roman period, there would have been about 4 meters of water above this, which would have been very threatening and probably washed it away if it was in an exposed land surface. So we know there must have been mudflats around it. And if we just go and we did a bit of project where we excavated that. We excavated one of the posts, and interestingly, in a post here, this is a Roman post, which can be very well preserved with cut marks on. Interestingly, the small one here turned out to be Bronze Age, going back and back to the sort of about the 3,100 years old. And we see a multitude of structures here. There's a Bronze Age structure at the beginning in the foreground here, a Roman in the background here, and that's also got Bronze Age material. So it's a whole sequence of people, a very important site that was occupied for about 1,200 years. Again, it would have been one that would have been sheltered and protected, probably giving a jumping off point to get over to the Isle of Wight, and would have been protected in marshes. But as you can see now, you're down to the geology, it's all gone. When we looked under the water, we did see going out slightly deeper and further in time. We're going back further in time as we go out to the Bronze Age here on the left at 1,371 BC. And then as we come back up here, slightly to the shore, we do get younger structures going to the Roman period. So that idea of going down the beach is sort of going back in time, even though this is slightly complicated in this scenario because we have mudflats and sheltered embayments, but we can take that. A lot of work's been done by Dr. David Tomlin on Wootton Core to demonstrate that. But we've done some work at Boulden-the-Cliff where we can go underwater. This is on the underwater at Boulden-the-Cliff. This is a bathymetric image. It's color contoured, so it shows you the different depths of water and the different depths of water, different colors. So the top here, you got minus about 4 meters below ordnance datum, dropping down here to sort of 11 meters below by this green motley area here. And we've gone down, you see, down the beach here, down underwater. And what we've got under here is a land surface that's actually 8,000 years old. So this is 10, 11 meters under ordnance datum, going about 8,000 years, and it's an area that's covered in trees. It's very similar to the ones you saw on the beach, but much older. So these trees here, going back to 8,000, 8,100 years old, they're just eroding out the side of the bank. This is quite important because these erode pretty quickly. So this is largely gone now, this tree, because the photo was taken a couple of years ago, but it shows you how quickly those banks are eroding away underwater. And of course, when you get these underwater landscapes going, then the water volume increases and then the energy picks up and it affects the coastline as well. But people tend not to look underwater, apart from archaeologists, maritime archaeologists. Archaeologically, it's very significant because of the preservation. And these here are some leaves, oak leaves, came from the site. Examples we found a few last summer as well. They date to over 8,000 years old, but you know, they could have been dropped in the forest only a couple of winters ago. So incredible levels of preservation. And this particular site was discovered by a friend in Lobster that we found living under an oak tree. The oak tree at the top here, again, about 8,300 years old, with bark on the underside. And it's been eaten away there with gribble because it's now exposed. But nice site because we went down. When I first went down to the site in the end of the 1990s, and I found this incredible submerged forest with these great big tree trunks and boles lying out on the seabed and all this vegetation, I thought, and the tree stumps sticking up. I thought, this is incredible. So we got teams together and we went down there looking because I thought there's got to be some examples, evidence of human occupation in this particular site. We looked for a couple of years, couldn't find any. Then we found the Lobster, and just in front of its burrow, it was kicking out all these little flints. And we started picking up the flints and looking at them, and we realized they were really fine, nice sort of Mesolithic, Middle Stone Age tools. People had been living there, occupying the site just before the sea level came in. And it's just an example of lots of the blades and bladelets on the right, and of course on the left you've got all the cores from which they were taken. Luckily, because of those wonderful chalk cliffs that those flint was being provided by past geology, has provided the essence for more recent human activity on the site, making the Isle of Wight quite a special place. And we found a bunch of tools underwater as well. These are adzes. These were used for chopping down trees. Process of climate change, of course, it was quite cold about 10, 11,000 years ago. Then warmed up, trees started coming in. And because you had trees coming, oak trees moving from the south and migrating north, and because you had more of a forested landscape, you then had the development of tools like this that were used as adzes and axes for chopping down trees, which became a bit more prevalent. They'd be hafted and you used them for chopping down trees. This is an adze, and these tools are actually more useful for chopping, making sort of planks and making sort of planks or boats and planks, or trimming wood rather than just chopping it down. Other sort of evidence we found on site, just to mention a few things, that there's this string, oldest piece of string in the country, sort of thing that you use to help by hafting, putting the handle on the adze head to chop wood. And then when it came to wood, the Mesolithic period, it lasted from about sort of 11,000 years ago to 6,000 years ago. So 5,500 years of people that lived in the country as the sea level rose. So sea level was pretty much rising all the time they were living here. So a lot of the areas they would have occupied would have been around the coast because they tended to be the richer ones with more resources. And unfortunately, all those, well, all that coastline is now covered in water. And so we're now finding this evidence, this woodworking stuff, underwater, very well preserved, but we got very little to compare it with on land. Maybe, you know, there's places like Starcar, but there's only about 120, 130, 140 pieces of worked wood in the country. Now we've doubled that just at this Mesolithic site in Boulder Cliff alone. But when we first saw it, it was hard to make sense of what was worked and what wasn't worked. And you can see these sort of ambiguous bits at the bottom. They're flat on one side and round on the other. Weren't quite sure what they were. But then amongst them, we get these really nice tight cut marks, which are sort of evidence of working. But it was hard to really make sense of them, or hard to make an argument that they really were worked without more archaeological evidence. And something we found was a big flat piece of timber. It's this one on the right here, that when it was first found, it was about 60 centimeters wide, a couple of foot wide, by 3 foot long. And it turned out to be a flat piece of timber that was taken from a tree, split tangentially. That could either be a massive plank. It was from a tree that would have been about 6 foot wide, 2 meters wide, and maybe slow grown, maybe 20 or 30 meters high. So it was a great big timber, or it was the base of a log boat. And with all the other work we've been doing, we found lots of burnt evidence of burnt flints, lots of worked timbers, lots of structures. The most probable, 99% sure, is that it would have been part of a base of a log boat, the bottom third of a log boat, let's say, and the bits on the side have been broken away. And around it, we had all these other different bits of timbers here, these big bent, all worked, strangely worked timbers, the like of which we hadn't seen because, as I said, the evidence just isn't really there. So we're creating now more of an analogue of these timbers, a reference collection that we can now use around the country. So I mentioned those sort of curved bits and round bits, and we've been finding a few over the last 20 years. But more recently, we found them in an organized way on the seabed. So here you can see these timbers here flat on top, and then they're round, there's a flat bit there, there's sort of a bit barking round on the other side. We've since worked out that they're all part of sort of bark and softwood from the tree, and most probably the result of, or pretty much definitely the result of trimming an oak tree. And while that boat was being made, they trimmed all the outsides, the bark and the sapwood. And as they did so, they had all the spare wood and they could use it to form platforms around this particular site. Now, because all this work is saying it's so, it looks very ambiguous, but then you come across pieces like this. We don't know what this was, but you can see all these cut marks are so clear, and burn marks. There's a lot of burning and charring. What they did to hollow out the log boat is they would have laid up some charcoal on top. We found lots of this, and they'd burn the timbers, and then they'd use those adzes I mentioned to carve them out. This was also a very significant time, and say the log boats irrelevant and appropriate because it was just before the final severance of Britain from mainland Europe due to sea level change. And some of the technologies they were using here are sort of more akin with continental Europe than they were with the evidence we're finding from mainland Britain. So the problem with the sites is underwater, we can't see it. It's very difficult to show to people because the solent can be quite muddy sometimes, as you're probably quite aware. So we've been working on the site more recently, and we've been collecting 3D models as well as sort of videos, but trying to reconstruct it. So this green area here is made of about 500 photographs all patched together to try and show you what the landscape looks like underwater. And you have these edges here, the shade, that's all to the north of that, or that's actually to the south, but above it, you have the peat shelf with all the trees and planks and wood and archaeology in it. And at the bottom, you have all this just eroding away. And every year we try and go back and record it. This is receding. That shelf is getting smaller and smaller. And it's an example of changes throughout the solent. The whole solent's getting larger. And on that particular site, I mentioned about these platforms. We've actually got, they're called WF wood features here. Over the years, we've identified 5 different platforms. This is the south, the light coloured bit. This is closer to the Isle of Wight, and the north is all eroding away. So we're finding them coming out to the edge of the cliff. And at the bottom, we have another one of those 3D models showing you, there's a tree there, showing you where some of these features are. This is where we found that the log boat, and here we've got some other wooden platforms. And only, actually it wasn't last year because that was a bit of a COVID year, but the year before we dived and conducted excavation of this area here where we found another platform, and there were about 60 pieces of timber all interwoven. Rather than just finding a dozen here or a dozen there, there were 60, and they were laid on top of each other, crisscross, and they formed a platform about 6 foot, a couple of meters across by a meter wide. We've modeled that, but these are all made of the same bits of timber that they've been cut from the side of an oak tree, and they've then been reused to create these platforms around the site. And I say this material is pretty unique, it's pretty special. It tells us a lot about the Mesolithic. It also tells us about how people responded to climate change and how they adapted to sea level rise as it flooded the Solent. But it's just being eroded away and it's just going. We're trying to do what we can, but it's underwater, so there's no statutory protection. So now if anyone wants to have a look at these models, you can just look at, go through our website or Sketchfab, and you can look at them and you can sort of spin them around on the screen. And we'll try and record them by preservation by recording, if nothing else. But something else that was really significant about the site was the discovery of wheat. And we did some cedar sedimentary DNA analysis on the site. It was published about 5 years ago. And we found wheat here, which is about 2,000 years ahead of any other wheat found in the UK. This would only really be viable. It wasn't grown here, I should say. It was a big lump of it. So it would have been transported and would have been most viable if you were using a logboat, of course, or going by water, because this wheat was being grown back in the steppes, not steppes of Russia, back in the North European plain, so quite a way. So there would have been connections, there would have been links, and people would have been moving quite quickly across those waterways from east to west. And just coming to the end here with a reconstruction of that particular landscape at Boulder Cliff, just as the sea level was coming up. And we have the logboat building construction at the site here. So I haven't given too much detail because it's a very short talk, but we got evidence of all this burning, all these sort of activities taking place. We know in the DNA there were dogs, so wolverine dogs, lots of rodents, also auroch in the back here. So they had, these are sort of wild cows, about twice the size of cows that were being hunted. And we got the auroch bone and auroch DNA. And it looks here, we have the wheat, and they would have been making bread. So it looks here like this lady is sitting by the fire, probably putting together the wheat and the bit of auroch to make probably the first ever beef burger known in the UK. But on that note, I will draw to a close, just to highlight the value of maritime archaeology, or highlight the value of archaeology and past landscapes, important in their own right, but they can also be used as datable markers to understand past climate change. Thank you.
Garry, that was amazing. Thank you very much indeed. Okay, well, now we've got a few questions, and the first one's to Steve, and it's about citizen science, a project called Go Coast or Co-Coast, and it's about the potential for people to join in with citizen science projects, mapping changes on the foreshore.
Okay, yeah. I wasn't directly involved in Co-Coast, but many of my ex-PhD students were, and ex-postdocs. So Catherine Bond was based in Portsmouth, and Nova Mishkuska was leading the stuff from the MBA. And I don't think there was a second phase of that work. I think one is planned at some stage. It's Heritage Lottery funding. But certainly the resources which were made available through Co-Coast could be used. And there was already some quite nice papers coming out of Co-Coast with data collected by citizen scientists in the various partner institutes, which were Portsmouth, the MBA, coordinated from Newcastle, Bangor, and the Scottish Association of Marine Science, and I think also maybe in Northern Ireland. So I still think there's lots of opportunities to do work, and I'm hopeful there might be a Co-Coast 2 at some stage. And now I'm retired and not wearing a suit as a dean in Southampton, I might get involved myself. So yeah, lots of opportunities. And you know, there's lots of good online resources. There's also books you can buy. I'll give a plug for Hawkins and Jones, 1992, which you can get dead cheap on Amazon. You know, there's lots of things you can do to go out and on the seashore and identify stuff. And clearly, I think the local hub on the Isle of Wight was being organised out at Portsmouth. So get in touch with the people in Portsmouth that are still there and see what else is going on in terms of residual activities. And tomorrow I'm on the shore with one of the COCOS people, Nova Mashkushka, and I'll ask her if there's any follow-up plans.
And do you know if any of the natural history societies around the place have had very active marine sections? You know, we're waiting for our Roger to retire so that he can help lead. We've got a division, a section, but yeah.
I think it varies. I mean, I think interests wax and wane. I mean, the great thing about the intertidal is all you've got to do. Well, the only bad thing about the intertidal on the Isle of Wight is you've got to get up bloody early in the morning to get low spring tides, or do the evening tide. It's much more civilized in Plymouth, where where the big tides are in the middle of the day. But the great thing about the intertidal is it's accessible, it's cheap, you can go out there, and there's lots and lots of resources to identify things. So certainly in Devon, the Devon Trust is for nature conservation is very active in marine stuff. The Cornish Trust are very active. I'm not so sure about the Hampshire one. And I know that your society has always been pretty, obviously a big interest in fossils, big interest in terrestrial stuff, big interest in archaeology, but there's always been a strong marine thread there. And I hope actually that Roger doesn't retire too soon, because it's good to have some of your former students still working and being able to do stuff.
Okay, and it was very impressive that there's 100 years of records based in Britain, and you just touched on a French attached to the Paris Museum, but how do they compare? Have they got as long a record and been as active, and have they perhaps kept people on, whereas we've been making people redundant?
Well, Eric Fisher-Piet was based at the Dinard. He was based at the Paris Museum, but the Paris Museum had a laboratory in Dinard. They still do. And he was actually a really, really good intertidal ecologist. He did some of the first experiments on rocky shores, and he also did a lot of broad-scale biogeographic stuff. He fell a little bit under a cloud during the Second World War, because I think maybe he collaborated a little bit. And was still publishing papers in 1943 rather than blowing up railways. But he did some really, really good work. And actually one of the people he mentored, a guy called Harry Atton, actually I think died in one of the prison camps during the war. And he did some of the first experimental ecology on rocky shores in Europe, where species were manipulated, you know, take one species away and see what the influence of that species has on other species. So there was a great tradition in the 1920s and 1930s, and even going back to the 1830s. One of the first descriptions of zonation on rocky shores was done by Audouin and Milne Edwards, published in about 1832. But then it sort of went back a bit. But now there's a new generation, and the French have got some very, very good data. They've got some excellent offshore data, better than we have in Britain. And they've been less affected by the kinds of cutbacks and things. I mean, an awful lot of the long-term work in Britain was stopped in the 1980s during a period of financial difficulty. And when I was director of the MBA, I restarted a lot of the work, and a lot of that work's at threat now. The funding has just disappeared. You know, and it was such a shame that Alan Southwood, who was a mentor to me, a mentor to Roger as well, was basically had to retire 5 years early. So yeah, I think we've had more interruptions. I mean, the Plymouth Times series if you look at it, it's like a barcode. You know, there's lots of good bits, but there's lots of black gaps in it. You know, some of it's war and some of it's funding cuts. And the first MBA funding crisis was actually in 1909 when Lloyd George set up the Board of Trade and basically nationalised marine research. And the MBA lost its lab in Lowestoft, which is now the CFAS laboratory. So, you know, it's a when I retire from doing fieldwork and my knees are really gone, I'm going to write a history of the MBA and look at all the different funding cuts and the history of marine science in Britain, because it is a very interesting interplay between passion and funding.
Yeah, we'll have to keep an eye on this because, you know, clearly things could move very quickly, kind of post-COVID, post-Brexit and all of that.
Yeah,
now,
I think a lot of funding is going to be affected quite badly post-Brexit. I mean, I had a huge amount of European funding and I supervised 20 European PhD students out of the 80 odd I've supervised. And I think the kind of joined up stuff you need to do to understand climate change, where you need to work from Norway all the way down to Portugal, is going to get more difficult.
yeah.
And things like Interreg, which was so valuable for the last speaker, Roger's involved in Interreg, those kinds of fundings will go. But anyway, you know, what's happened.
Okay, we've got a question, specific question for Martin from Cat. You may have seen this, Martin. It says, can you describe the conditions when the Wealden beds were deposited, please? A bit of detail explaining how terrestrial led to those beds being deposited.
Okay, essentially most of the Wessex Formation deposited on land. Now, what that actually means is it was deposited by rivers. Okay, the environment of the Wessex Formation is floodplain. Now there's some discussion as to the precise nature of those rivers. Some of them may be what we call braided rivers, so that's intertwining rivers. Certainly some were meandering rivers, so that's the classic bend. So what would actually happen is that in the seasonal climate that it was a warm Mediterranean type climate. We were on par with North Africa, sort of southern Spain at the time. So it was a warm seasonal climate of probably cooler, wetter winters. Now the wetter winters would lead to floods. The rivers would flood and spread out across the ground. So when you see the classic Wealden Wessex sections of reddish, purpley coloured rocks, they are floodplain deposits. So it's the result of the river rising up, flooding out across the landscape, and then soil formation on top of them. The other common setting within the Wessex Formation is what we call the plant debris beds, and they are probably the result of very rapid floods. So in part, maybe there were levees along the riverside, and the levees breach, and then you get a flood coming out. Maybe they're also the result, in some cases, of oxbow lakes formed as a result of the cutting off of meanders. The other setting that we find within the Wessex Formation is sandstones, and those sandstones are what we call point bar deposits. So they are clearly related to the meandering river. So they're formed at the point of the bar. As the meander goes round, they're formed this side. And that is a very common setting for, say, footprints. So that tells us the dinosaurs were actually living there because the footprints are there. And you're probably, you know, somewhere like Hanover Point is one of those settings.
Oh, thank you, Martin. That was very comprehensive. A couple of questions for Garry. From Avril, was the inundation of the Solent gradual, or is there evidence of catastrophic flooding?
Yes, the inundation was very gradual. It's still happening today. Research we've been doing over the last 20 years, and also the University of Southampton as well, Collins and Key, have identified that it was pretty much an estuary until about 2,500 to 3,500 years ago. And it was really the break at Hurst Castle, between Hurst Castle and by Fort Victoria there. You had the break there that probably overtopped about 2,500 to 3,000 years ago. Slowly, and it's still continuing today. So it's a process that's ongoing. So nothing sort of broke through, it just overtopped it, and then the tides picked up back and forth, and slowly been eating away and taking it down to what we see today, which is why a lot of the erosion is happening. And that's why Hurst Castle has just fallen into the sea, because they put a castle on the end of a spit that probably shouldn't really be there. And the spit wants to move, but it can't because it's got a castle. So, but it's an ongoing process. It's been quite interesting. And we know a lot of that because of looking at some of the sediments at Boulder Cliff. We've looked at some of the older sediments and they've got the green sands in. And then the upper sediments have got more material that's dominated from the sort of the Hampshire Basin. So we know that the water has actually come out the River Yar. The sea was coming out the River Yar, filling in the Western Solent from about 8,000 to sort of 5,000 years ago. And you can see it in the sedimentary archive where that was coming. And then there was changes to the east and then to the west. So no, that was so it's a long-winded answer, but effectively it's quite the story of the Solent is something that seems to be not understood too well by a lot of people, but it's very relatively modern phenomena, and people should need to know that because it's still forming now.
I mean, thank you very much. And isn't it true to say that understanding on this is relatively recent? Didn't people think very differently until not so long ago? That there was
there's the belief that the Solent River all the way from Christchurch, yes, and in fact that video I gave you was about 20 years ago, which is slightly inaccurate at the beginning for my scope pack. Yes, there was the idea of a Solent River, looking at some of the terrace deposits. But say again, as work by University of Southampton, a paper by Radiometric demonstrated that the geology is only about 20, 30 meters deep when you by Hurst Castle, they're just going out into Christchurch Bay. And basically the river would have had to come uphill and down again. And it goes relatively shallow. They're deep by Hurst, but the river couldn't have gone up there. They would have headed south beforehand through the chalk.
Yes, no, very.
So that's only the last 20, 30 years.
Yeah, very interesting. And I think if you took a type of straw poll of people on the Isle of Wight, you get some very different answers as to when we were last joined to the mainland and how. But now Rosie's asked, how often are you finding all of these things? Do you collect them or leave them where they are?
You find them, like found some more this afternoon before I rushed here in the northwest Solent. You're finding them all the time because these mud flats are eroding away. If you look, you'll find them where there's been these sort of mud flats that are several thousand years old. They're now going. So when there was archaeology underneath, they're there. Now, whether we can rescue them is something that, well, not really. We try and rescue what we can and preserve what we can, but we're just a charity trust. And as you mentioned at the beginning, we were the Hampshire and Wight Trust for Maritime Archaeology. And we were set up by those councils because they didn't have a remit underwater. So they set up an independent charity to go and try and do that work because they can't spend taxpayers' money, on an area that they haven't got responsibility for. Now, of course, all that funding we had from them is gone. And so we survive on various projects from Europe, or did, and the like. But now, so now we do what we can. We try and raise some money to support and save it. And of course, we put it in the Shipwreck Centre and Maritime Museum in the Isle of Wight as well, in Arraton, in the middle of the island. So people can see preserved materials there, that we do try and preserve what we can. But generally, all this is being lost because there's no funding or resource to protect it, because there's no statutory regulation to protect it.
Yes, and I must say you've got a very impressive website that people should think of looking at, and as you say, the Centre at Arraton Barnes.
Yes, there's a prehistoric display there looking at sort of climate change and how the undulation climate and how people came to the Isle of Wight, and the Isle of Wight built the first boats in the world and all sorts.
So there's a question here. I'm aware of the terrestrial restoration ecology projects currently on the island, but how important is the restoration of marine ecosystems for helping with food, elevation, sea level rise, and what projects are currently going on around the island?
When I was working in Southampton, which I did until 2016. I was also involved in a big European project looking at flood risk, and we were doing work in various places, including the Hampshire coast and also Bognor Regis. I mean, at the breakwaters at Elmer in Bognor Regis, we've done a lot of work on. So my view is that if nature can do the job for you, don't mess around with it. And I think it's really important to maintain salt marshes, which provide quite a lot of wave attenuation, and similarly seagrass beds. There's some seagrass beds at Ryde on the Isle of Wight, which do attenuate waves. I've just had a PhD student that finished just before Christmas, who was working on the role of seagrass beds in trapping sediment and also in attenuating, in actually dampening wave action and acting as natural coastal defence. And a lot of my colleagues at NOC in Southampton have worked on that over the years. So it's really important that you keep salt marshes, it's really important that you keep seagrass beds, and both of those are at risk from various threats. I mean, it's really interesting that the seagrass bed at Ryde gets completely interrupted by the hovercraft. You can actually see from aerial photographs where the hovercraft is going up and down and affecting the sediment dynamics of the shore. Not surprising, really. So yeah, it's important to restore marine habitats, but if you've still got to deal with coastal erosion and you build groins or sea defences, then they can be done in a lot more sympathetic way. And Roger and his team in Bournemouth are doing a lot of really good work on that. And in the past at Southampton and in Plymouth, we've done stuff on that as well.
Okay.
So, you know, nature's good, but sometimes you really do have to build concrete, but you can do it in a sympathetic way.
A very big thank you to our three speakers this evening. Thank you for everyone for taking part. Three special thank yous. First of all, to Tina Whitmore, who's done a lot of clerical work in the background. Then to Joe for this evening. That's been, thank you so much, very professional and really helpful. And a big thank you to Roger Herbert, who has got the speakers together and you know, put the programme together. You know, so it is down to Roger. So thank you all for taking part, and enjoy the rest of your evening.
Thank you.